Thank you very much, colleagues. This is Mike Anthony, Greg Walson, and Christine Fisher. Um, we are in two time zones today. I'm at the NFPA conference in Las Vegas at the moment. We have the privilege of Greg Walson from MIT, who will be giving us a broad brush overview of the MIT power system. This is something that was requested by Lauren and Ahad over the past few weeks. They're not in right now. It's actually out of their time zone. They'll generally call in the American session. So this is nominally the European session. We don't have any, we don't have Giuseppe or Reinhard or anybody calling in from the European Union. So we're going to get ahead on this. We'll be recording this and making it available for the afternoon session. So I'm going to cut to Greg immediately, but I think maybe first, I think everyone knows Christine. I'm going to let Christine say a little bit about something about herself, and then Greg, and then we'll cut over to Greg's presentation. Christine, you want to say a little bit about what you do over here?
Thank you, Mike. Good morning. Working with Mike Anthony on Enterprise. Advocate on behalf of the facilities industry, and I in particular help with research and
Okay, that's Christine. We don't have a photo yet for you, Greg, but hopefully soon we will. You want to say a little something about what you do there, Greg?
Sure. I started at MIT in March, actually, and my title is Senior Electrical Engineer. I'm one of two in the utilities group. Our purview primarily is to maintain the campus distribution system. The utility group maintains both the electrical as well as the steam, medium temperature hot water, chilled water facilities. And I put together this very brief slideshow just to give some kind of overview of campus as it is and was, and where we're thinking about going in the future. So, as everyone who does a PowerPoint does, I'm giving you sort of the outline of what I'm going to be presenting. I've got some basic facts about the Institute, which is what we call ourselves. I've learned where the campus was historically, where it is now, a little bit about my department, and then a little about our systems and where we're headed. So if you want to flip to the next slide. Okay, so MIT was actually, whoops, too far.
Okay, let's see if I can take us back to, there we go.
There we go. There we go. MIT was actually incorporated in Boston in 1861 and spent the first 50 years or so there. And then one of our presidents, whose name escapes me right at the moment, had a vision of moving to Cambridge and expanding the campus. Basically, his goal was to put all of the disciplines into a set of interconnected buildings so that they could collaborate more than was traditional at most universities at the time. So they built 11 interconnected buildings, and they built themselves a power plant. And now if you flip to the next slide. So those buildings right in the center, this drawing is actually from 1929, so there's been some buildings added from the original. But those core buildings in the center there are primarily the 11 buildings that were originally built. What's fascinating to me about this picture is up just above where the core buildings are, there's a test high tension line set up, and underneath it is a rifle range, which I find kind of amusing. Yeah, right about there. Anyway, if you flip to the next slide, you will see what we look like now, which is obviously much different. As you can see, Cambridge has filled in just a little bit around us, and we've added a fair number of buildings as well. And the irony, of course, is that up until probably 20 years ago, even this whole area was either factories or parking for people going into Boston. And since then, it has become quite a hub of biotech and new research and various other things. So, next slide then. We have now 168 acres spread about a mile along the Charles River here in Cambridge. I count about 150 buildings, depending on how you count the buildings. Some of them are interconnected, so it's debatable. And then we have about 40 other buildings that our department's responsible for that are not on the main campus. We don't take care of Lincoln Labs. They're their own sort of entity. We have currently a little over 11,000 students and a little over 12,000 employees, which I also find kind of interesting. We have more employees than students. Maybe that's typical for a university. I'm not sure.
I think the larger research universities, that's the case. Yeah.
Yeah.
Back up a bit. Are any of your
Go ahead.
buildings in residences? Harvard still is. There used to be. In fact, the Kennedy Center used to be in the one they built over there closer to the river. Used to actually just be in a house. I mention that because there's a lot of regulatory activity dealing with residential, and it's tempting to dismiss these what I'll call peripheral facilities as residential, and it's not part of a campus, when actually the stewardship of those residences, what amounts to really a resident, even those businesses going on in them, is affected by, frankly, the international residential codes.
Mm-hmm. Well, so as I understand it, we have 18 residence halls. Those are primarily large volume, or at least multi-unit buildings. There are some they call independent living collaboratives that are affiliated with the university. Those also, though, tend to be either small apartment buildings or sometimes even bigger ones. I'm not aware of any that are actual residential houses, but that doesn't mean there aren't any. But it is an interesting point you bring up, because we're actually in the process of building a new dormitory, or sorry, I shouldn't say building, design for a new dormitory. But the ground level of it is going to be retail, and we're getting into some of those issues about where does the code stop and whose code do we have to follow, and it gets gray at various points. Not to mention the fact that we're a nonprofit technically, as you said, and we can't necessarily have retail. So we have an entire division called Matimco that is our investment arm that handles anything that makes money, basically. And I guess they manage the endowment then somehow. Mm-hmm. I don't know if that answers your question.
It does.
Okay. So this is sort of a broad overview of the campus. You can see how we kind of go along the Charles River there, and all the yellow buildings are buildings that are somehow associated with the university. Those core buildings are just right in the center there, and that's considered the main campus, I guess you'd say. So go ahead and flip, if you don't mind. I'm in specifically the Department of Facilities. We have a little over 600 employees broken into 3 groups: campus construction, campus services, and maintenance and utilities. Planning used to be, I believe, part of campus construction. It's actually been broken out separately now. I'm in the maintenance and utilities group specifically. You can flip, Mike.
One question. Do you have a separation between the organization that is in charge of renovating construction and building new square footage, and an organization or a sub-part of the organization that deals with O&M? We have that here at the University of Michigan, where I think they want to deal with the money differently. There's different, there could almost be different cultures between the operation and maintenance and the plan extension, we used to call a plan extension. Different type of money flows through them. Can you comment on that?
Yeah, so we have my group, maintenance and utilities, includes both the group I'm in and then obviously what we call repair and maintenance, which is maintaining buildings. We have a separate group called the systems engineering group, which handles refurbishment and design of new buildings. They're under a separate director. There's also, and now the acronym is escaping me, we also have another group which is separate from those two, which actually manages some of our newer buildings, which is more of an integrated group where they do a little more of the planning and maintenance of the building internally. But that's sort of a newer thing that I'm not really involved with. But yeah, we do keep those things separate. And part of that is because a lot of the R&M folks are union, So they're under a different type of contract.
Mm-hmm.
I am not, but a lot of them are.
Yep. Yep. Okay.
Okay, so let's see, what was my next? Okay, so just talking briefly about our electrical distribution, I'll clear up one common misconception that a lot of people ask me. We do have a fission reactor on campus. We do also have a fusion reactor on campus, and neither one of them do anything to generate electricity for us. There's still a lot of people in the area who think that we use our fission reactor to supply our power. It's actually rather small and doesn't even have any equipment to generate steam. Actually, I believe it doesn't even get hot enough to generate steam. So
it's largely instructional. We have one of those here also. Yeah. Or yes. I think some of them actually were for a while. I hope I'm not speaking out of turn here. We were actually preparing isotopes for medical and clinical purposes. Yes,
we were doing quite a bit of it. We actually did some treatment, I believe, on site. They have a facility. They have a room underneath. I've seen it. It's underneath the reactor where they could direct a neutron beam at a patient. That has stopped for a lot of different reasons, I guess. We also used to do a lot of silicone enrichment to dope silicone for circuits, and that has also moved off to other facilities because sorry, I'm getting rid of my sound again here. The reactor cannot dope sufficiently for the current commercial needs of customers. Let's see. So we have two electrical systems on campus. We have a 13.8 system, which is a newer system. We bring in 6 lines from our local utility, and we have a 20 megawatt cogen turbine, natural gas, and fuel oil. We have 2, I want to call them substations. They're switch racks, and they supply 6 normally open loops. So basically, each loop starts at one of the stations, runs through with a normally open tie in the middle, and then back to the other station, so that we can backfeed a loop if we need to do work on a piece of it.
That's fairly common. So effectively,
yeah.
You're running a radio. You're normally
yes.
we see
yes.
in the meetings. In the meetings, we say a loop so that we can get money to make sure that we can move that switch
yes.
around. But we're actually operating radially, except
Correct.
contingencies. Yeah.
Yes, and we're not at this point. We don't have the ability to automatically close a tie. They're all manual switches. So that's something we're looking toward down the road, but we're not there yet.
So this is important because this affects a lot of the regimes. So let's back up a minute. You're running. It looks to me like you're running a grounded system on the 13.8
yes.
and ungrounded on the 2.4.
No, they're both solidly grounded. You had asked me that, and I looked into it.
Okay.
I believe that they are both solidly grounded.
Okay. And who's your utility there? Is it?
It's it's called EverSource now. It used to be NSTAR. Okay. When they merged with Northeast Utilities, they changed their name.
Mm-hmm. So when you need to during a contingency and effectively do the loop, you need to balance the voltage across both of the incoming buses?
Correct. We actually have one bus that the 6 loops tie to, and then that has 2 feeds into the campus system.
Does the utility let you balance the voltage yourself, or do they want their people to come in?
We are able to balance ourselves. We have a voltage regulating system as part of the cogen, but we do follow them. It's not,
Yeah.
But we do it ourselves, yes.
And go ahead.
Go ahead. Sorry.
So you'll likely have a supervisory circuit between your utility. What's the utility called again? Your
EverSource.
EverSource and your cogen. You're basically picking up with their thermal load. You're picking up whatever. Actually, your thermal is your base load. Is that right?
That's generally the case. Our directive now is actually to run the cogen at whatever is the most efficient from greenhouse gas perspective. Mm-hmm. So we look at and also it used to be price, now it's greenhouse gas. So we look at what we can generate. Currently, our cogen is more efficient than the average power on our grid here in New England.
Mhm.
And so we try to generate, but we also do it based on thermal load. So, typically our campus load runs most days in the mid-20s. In the summer, it might go up to the mid-30s. And I'll see the turbine running 15 or 16, and then we'll bring the rest in. Some of that's going to change, and I'll get to that in a bit. We're changing our cogen system.
So that's interesting that now we have a new equations that, first of all, can you condense? Can you, for economic advantage, do you have like a dump condenser or balance condenser?
That's a good question. I don't know the answer. I'd have to ask.
Okay, so what it does is that in order to get an economic advantage, you actually will condense your steam through, I'll call an auxiliary, it's almost like a load bank when you're testing your generator. But when it turns out your price for your natural gas is low enough and it's more economical, maybe it's a couple pennies for you to generate, you've got to get rid of the steam somewhere. And you're roughly in the same climate zone as we are. So you probably find your fall and your spring thermal relationship a little bit dicey if you're trying to save money.
Yeah, I think that's true. We actually have a company that wrote a software, I don't remember the name of them off the top of my head, but they wrote a software program that basically takes all the variables and tells the operators how to dispatch the plant most efficiently.
Oh, that's funny. I hope you didn't pay too much. Hope you didn't pay too much for that, because that was my senior project in engineering school, and we did it on VisiCalc. Well,
I have no idea.
What did we call it back then? It was a little simple. It was pre-Lotus. It was pre-Lotus. College, 21, 22-year-olds, and so now you've got a bunch of glossier consultancies that roll in. But you can turn a senior on that kind of a problem if he's had engineering economics.
It's good.
But I'm sure
it's good to know.
Why have the students? Why have the students do it when you can pay a consultant $100,000? Yeah.
Oh, absolutely. Yeah. Got to keep the consultants in business. I might be one again someday.
Yeah.
You never know.
Okay, and I guess the follow up is that with your supervisory circuit, is it a so between your utility and you,
we have fiber optic for relaying and I believe for supervisory.
Is it redundant?
Well.
Do you have like a
I believe it is. Yes, actually it is. We have two paths that go back via different routes.
Yes, and then dump the whole bus when you.
You're talking about island and.
Well, no. Suppose so on your bus you've got more load than your generator is going to pick up. Excuse me. Then so you lose the utility. And
right now the way our system unfortunately is set up, if we lost the utility and the campus load was greater than what the turbine could take, we would go black.
Yeah. Okay. That's a common thing. That's the other thing the consultants will want to sell you.
Oh yeah.
Which is not to say that it doesn't work. I know of places where, and I'm not sure whether it's Texas or Berkeley or Washington, where they are actually running in parallel. A lot of it depends on whether utility will do it, but a more common configuration for at least most of the utilities up here that prohibit you from they have certain prohibitions on your transformers that you go black.
Yeah, I mean, so normally we are running in parallel, as I mentioned. We parallel with the utility, but I'm going to get to in a couple of slides. We're actually in the process of two different projects that are hopefully going to help that situation. I can talk a little bit about them in a minute.
Okay, I don't know to distract you, but that this cogen, the reason it's important is that I'm not sure that this discussion occurs, say, at the International District Energy Association. I think they're aware of what it means when you dump a load and you exceed your generator's capability. I think they get that. But we found that most of those ideas and some of the subtle trade-offs that you have and some of the restrictions of the utilities and, frankly, the risk profile of the people who are managing the plants as opposed to electrical engineers, that these end up being these are some of the areas where we'd like to investigate it a little bit more. It seems a cultural condition that they would rather the utilities for their purpose, because they have a wider purpose of serving, the entire city of Cambridge and Boston, for example, that they're going to dump you, and you're on your own. You see, because it affects you're just another service for them.
Well, so that's actually an interesting point that you raised that, because we're actually in the process of, as part of our new project, retying some of our lines, and we in the process asked for capacities, and I'm not going to get into too many details, but let's just say that the utility is fairly conservative. Having said that, they have also told us that they would make their best effort not to dump us. I mean, if a particular one of the feeders overloaded, they would not necessarily shut it off, because it would be a cascading effect. And they've already had some bad publicity about losing loads in this area, and losing MIT would probably not be great publicity for them. But I shouldn't say that on a recording, but anyway.
Well, no, we have it here. They have an obligation. They're, as I say, we're an industrial customer, and unless you've got a hospital, and I don't think you do, that
we have a medical center, but I don't know that they're inpatient.
That's right. So you're not on the priority list when they do their load shedding.
This is true.
So that's the difference. Whereas here at U of M and a lot of the research universities have hospitals, and you are on their priority load shedding list. So these are actually some of the fine points we need to get right. A lot of our not this teleconference, but you'll notice that on our website we have a list of technical issues to discuss. And where is it? At what point do we say, a load shedding regime is economical for you? A lot depends upon the interruption, the reliability profile of your area, and maybe, I don't know, what are you losing it 1 or 2 times, 1.2 times every other year, something like that? I mean, how often is it happening for you?
And luckily, at least at the moment here, it hasn't happened that I'm aware of particularly often. So that's, although we will, we do work with them, and my understanding is if they were having issues, we would do our best to shed load here on campus as much as we can.
Yeah, do you have interruptible incentives there? Do they say in some of your other buildings?
We aren't at a point where we can necessarily dump an individual building. We would probably dump chiller load and some things like that first, and then have to see where we went from there. It's one of the things that I'll come to that we're trying to work on, is the ability to more easily load shed on campus.
This particular area, I'm going to let you go on. This is these fine economic reliability was one of my specialty, and I'm going to let you talk about your system here rather. Should I click the next slide?
Yeah, you can go ahead and do that. Sure.
Let's see if I can remember how to do it. There we go.
Okay. I'll just give you some brief numbers on the steam and hot water system, and again, this is not my area of specialty, so I got this from a publicly available document. We have a HRSG on our turbine. We have 5 steam boilers. We supply the campus with 200 pounds per square inch steam. I've been told we have at least 10 miles of piping. Nobody's exactly sure. A lot of it's in fairly worn shape at this point. We have 4 buildings that actually use medium temperature hot water as opposed to steam. We convert the steam, and this year, for the first time, we are no longer using fuel oil for any of our normal operations. We are keeping some for emergencies, but at this point, we've stopped using it for normal, and that's part of the MIT greenhouse initiative that's been going on. We set a target for, I believe, 2030 to have our emissions down to 1990-something levels. I should know this better, but I don't.
Are you testing? Are you doing any periodic testing or any testing at all of that?
It's a good question. I think we're doing it more mathematically than we are necessarily actually going and checking emissions directly. if that makes sense.
Well, no, you've got pumps to move. You've got
Yes.
there's certain the oil has to be. I mean, you can't. This is not my area. You have to treat the oil, of course, and how often you do that. Generator testing ends up being using the backup systems, whether you're once a year, once every 3 years, or once a week. All that stuff.
Right. I believe we test our backup generator about once a year. Again, that all falls under the utility plant and they're a separate group, and they sort of do their own thing. So I don't know a lot of exactly what they do.
So the fuel oil is for the boiler, right?
But well, yeah, we can actually run our turbine on it if we need to, but we try not to. And the boilers also can run either natural gas or fuel oil.
Yeah, that's the system I'm referring to. Yeah. Okay.
Yes. Okay. So let's see the next slide.
Oop, did I miss one?
Far.
Here we go.
Yeah. Just briefly, for those who are interested, we have 6 steam-driven chillers, and 6 electric motor chillers, and we distribute chilled water at 42 degrees Fahrenheit, for anyone who's interested in that. Okay. And I think the last slide is talking a little bit about the future. So we are currently in the process of adding to those chillers 2 new ones, and we're adding several cooling towers to deal with that load. Those should be online very shortly, actually, probably by the end of the summer. We are in the schematic design phase of a new cogen plant that we're going to be building, and the plan is to have 2 21 megawatt turbines. Our 20 megawatt current turbine is going to be retired. It's actually at end of life now. And then we're going to, going back to that loop system we were talking about, we're going to add 2 additional buses so that our loops will start at the old system and end at the new system for additional redundancy. In part of that project that I didn't mention on there is we are coordinating with Eversource Gas to put in a step-down station at our building so that they can bring high-pressure gas for us, but also for that it can be stepped down and used in the community to back up their systems. So it's sort of a collaborative effort with them.
Oh, that's interesting.
Yeah, it was one of the ways that we were able to get them. We basically will have at that point a non-interruption guarantee. That's the goal. So because as I'm sure you are aware, New England is having some issues with natural gas availability during the winter, and we want to make sure that we can run our turbine when we need to, as well as our boilers.
So there is a precedent out there for a campus district energy system providing contingencies to the surrounding community.
Right. I mean, it'll basically be their system sitting on our property. They'll own it and maintain it. But it was one of the it was one of the negotiations in asking them to bring high temperature gas to give us a more continuous supply. We have a fairly continuous supply now, but to make it even more robust, the agreement was given, okay, you can then step that down and redistribute it from here, and that'll back up some of your distribution in the Cambridge area. So that's good for them.
So it's just a matter of some pad, right? You need some switch gear and maybe some relaying and such and so forth, right? It's not a
You're
big...
talking about for the gas or the electric?
No, the interconnection. I think what I just heard you say is that you provide a backup contingency to the...
Yes, that's for natural gas, not for electric.
Oh, I'm sorry. Okay.
Yeah. I will say that we are looking at whether we want to, once we have 40 or 42 megawatts available, whether we want to try and sell back any of our extra capacity. And without getting into too many details, we probably won't be dispatched, but we might work out another agreement with the utility. And then going back to what we were discussing about the loops and load shedding, we're in the process of early stages of a project to recircuit the campus 13.8 kV system to better allow us to, first of all, to use this new station that's going to be going in, and also then to better be able to shed loads if there's a situation where we need to do that. Right now, a lot of our loops have multiple types of buildings on them, and so you have research facilities that really can't afford to lose power, and you might have a dormitory where you'd like the students to be able to stay, and then you might have an athletic facility that you might be able to lose, but you can't because the other buildings on the loop can't go away. So, that's some of the thing we're looking at. We're also in the early stages.
We think we have some solutions for you, but I'll let you finish.
Yeah, and unfortunately, we're not at a point where we've automated our system, so we can't dump an individual building without going out and doing it ourselves. So, or the electricians doing it. But, we're also in the process of looking at replacing our steam system with a medium temperature hot water system. I don't know the degrees of that. I think I heard 150 degrees, but I might be wrong about that. That is supposed to be more efficient and less issues with distribution of the water. And then we are very early in the discussion of the possibility of doing energy storage on campus and being a place where that can be tested a little bit, both as for electrical storage, but also for energy, hot water and cold water storage, energy storage. So that's where we are at the moment.
That's a lot. We have some solutions. I'm very glad you called in because this gives me a chance to get on my soapbox with a respected voice. I should say that I actually took my differential equations class there way back when dinosaurs roamed the earth under, I used to call him Nino Rota. He wrote the book on differential equations. He was, and I was a student of Arthur Maddock, the famed and legendary Goodwill Hunting guy. So all that said, there's some solutions here that are sort of on our docket, and I'm going to leave. If we go, I'm going to go over, if you don't mind. We'll come back to this. We do. So, for example, the problem of mixed load on a given feeder does complicate the load shedding. We get that. So what we've done here is we've kind of put together, and if I can find this, a kind of a blue sky. Here we go. We're looking for authors on particular issues. So one of the reasons we've dwelled on aluminum cabling so much, and this in the 2017, I think we put the nail in the coffin. My colleague Crystal Hunter and I put the nail in the coffin on all the objections to aluminum cabling, even at the medium voltage level. We know it's a cat fight with the Copper Development Association. Not cat fight. What's another word to say it? And here's where aluminum wiring in campus power distribution systems. When you are able to run a backup feeder or even a normal feeder for 2/3 less than copper, that's a big deal. That's a big deal. And so what does that do? You're going to be governed by the site, the location of where that building's going to go, where the building's going to go. You're not going to think, they're not going to ask, they may ask, but it's very unlikely to ask, where's the optimal place for us to put this? Some donor just rolled in with $200 million, we need to plop a building here in his name. And how do we get power to it? And is it cheaper to put it over here than there? And of course, your answer will be, we can do anything, right? With enough money. But you may be, to some degree, not to a large degree, you can solve some of that with aluminum wiring, and you could keep, say, office buildings on a given feeder. You wire up, say you've got, what are you using there for cabling? 350, 500 PPR?
350 flat strap. 350 KC mill.
Okay, so that's generally about worth 7 megawatts. And so, or MBA. And so, you can wire them up to some degree. So whereas if you might have had 6 or 7 buildings on a feeder, or even more than that, you might have, and you could actually define the load class. So there might be other reasons for using aluminum wiring, just the cost itself. Now you're limited by your duct, and
that's the biggest issue for us.
Right. Now,
And on top of that, my understanding, and maybe I'm wrong about this, is that you need a larger profile cable to carry the same load as the equivalent copper.
we get that. We know that. We saw that coming. And that's why we bore down on the transformer sizing. I will bet that out of every 7 megawatt feeder you've got, or I'll say it's 7 MVA feeder that you've got, I will bet that none of them ever get above 2.
Probably, that's true. Yeah.
Why is that? Why is that? That's back here at NEC, 220. That's the thing that we're working in the building premises level. Now, everybody needs to be able to feed that farthest load. You need to be able to run everything on that. You may be run open, normally radially fed, but when you lose the cable right up near the throat of the bus, you want to be able to swing everything down over to that one feeder. And I do get that. You don't want that feeder running any more than, say, 80%. Or maybe you can go 100% for a while if you think you can fix the feeder in a few hours. But that much said, our feeders are too big, period. And the consultants are way behind. Who's your consultant? You don't have to mention the name, because I'm going to give them a hard time. What?
We have a couple of them.
Yeah, all right. Well, tell them.
With regard to the underground system, it's a lot of it. Well, go ahead. Sorry.
I just tell them that it ought to be looked into. Probably you're going to get more bang from the buck running aluminum within the building. I don't doubt that. But to some degree, aluminum wiring. The other reason is aluminum wiring allows you to run a backup feeder at low voltage much cheaper. So, for example, if you're serious about greenhouse gases, you can do what I did on U of M's campus, which is I took 5 generators and turned them into 1. Because I was able to, because I was able to run that backup feeder with the appropriate control switchgear, 1,200 feet, as if it were only 300 feet away, or 400 feet away. So that's a big deal. So aluminum wiring solves some of your problems. But it doesn't solve all of your problems. The larger we have to get, and we actually have made progress. You'll notice in the 2017, you're going to see a lot. You're going to be able to recalculate your lighting load, which is 40% of your load anyway, to even lower than it was before. Okay, another thing that you give your consultants a hard time for, and ask them if they sit on any code writing committees. They probably don't. Is the idea of grounding, of resistance grounding. I don't think I have to tell you that that there's many benefits to being able to keep that fault current down for safety reasons, but also you can't with the appropriate instrumentation, you can pick up a face-to-face fault and you can have a few hours, maybe even days notice when your cable's leaking, and you can get in there and schedule an outage. And one of those outages could run you $100,000 an hour.
Sure.
An outage here at U of M, I calculate 100,000 to $1 million an hour. And so what you'll run into is that whether your EverSource will allow you to have a grounding resistor on their service transformers, but you ought to look into it. It's being done.
Yeah.
It's already being done at. We are an industry of precedence. Jerry Jimenez over at University of California, Berkeley has a resistance grounded system, and it works fine for them. They've had it for decades, no problem. We're trying to get a path set up where you can actually migrate from a solidly grounded to a resistance grounded. So I'd be eager to talk to your engineering consultants, but too often what happens is they're retained by architects who say, keep that fee low, and I'll just do what the code says. And they won't, because they're trying to make money, right? They won't really go too far off the beaten path. Ideally, they just change the title block on one job. They change the title, and then they resell it. And make a few changes here and there, and that's an ideal situation for a consulting firm. But to get new ideas, that's why it's so hard to get these new ideas. And your frontline people, your AEs, they don't really want to do that much different. That's why you see so few of them on the standards writings tables because they're in the business of making money. They don't want to assert. A good consultant can argue either way. So I'm just offering a couple ideas of the agenda of this particular, of our particular committee for any university like MIT, Research University, if it's interested in looking down the road and how this might, how they can contribute to making the campus safer, simpler, lower cost, longer lasting. These are already in process. Getting your building, and we're working on them more or less systematically. We're getting that building load, that power density, instead of designing it for 12 watts a square foot. No one has ever seen more than 6 watts a square foot for decades, and yet we can't get the code. It's taken this long to get the code changed so we can get it more rational, and that's what those papers were all about. So I would challenge it ought to be the normal course of business that when your AE, your electrical engineer, comes in and says, I want to build this for 20 megawatts, you instantly, or I want 8 new substations, all 2,000 MVA, kVA, right away you say, why can't they all be 750? That should be your first order of business.
We say that anyway, but that's called value engineering.
Yeah,
it's something different.
Yeah, okay. Well,
and by the way, we also get, can we put a double-ended substation in with just one transformer? So, because it's cheaper.
Right, I get that. Right, so here we are at MIT. Let's give it one last look here. It looks like I got somebody from the Department of Energy calling in a few minutes. I guess I'll have to get my game face on for that one. So
yes,
I'll have to. But it's been a pleasure here. I wish I wanted to get in so I could see the courtyard.
The Killian, yeah.
So this is where I used to hang out with my buddies, and we used to, right here is the library, and you could open it up and actually see people below, and you could drop stuff down.
Yeah, he was saying, well, they still put stuff up on the dome. A couple weeks ago it was a Captain America shield. So,
okay.
But I don't know if you know the story, just quickly, that Killian Court was originally supposed to be a reflecting pool.
Oh, no kidding. I didn't know that.
There's a very interesting exhibit actually going on right now for our 100th anniversary of moving across the river. So.
Oh, okay, yeah. So do you still have that tradition? I haven't. The tradition of interrupting the Harvard-Yale game? It used to be one year you guys you actually dug a trench. They trenched right in the middle of the 50-yard line. They blew up. You heard about that one?
I've heard about that one happening recently, but I think that students are the tuition's gotten so high they got to get the degree done. They don't have as much time to do tax.
Yeah, that's funny. Well, okay, Greg. I can't thank you enough. It's been a little bit longer, but I think enlightening. Yeah. We'll upload this for our American, Canadian, South American colleagues, and within a few days here. I have to log off because I have to get the meeting downloaded for the next meeting.
No problem.
So that's it. I will see you. I'll see other colleagues later on this afternoon, and the next one will be June 28th, and we'll try to get our normal. Agenda going. Obviously, we've jumped the agenda here, but this is more important for us. So thanks very much, Christine, for your patience, and Greg, and I will see you at the very least in a couple weeks.
Okay, sounds good.
Yeah, bye-bye.
Thanks, Mike.
Bye.